some variations to begin. Okay, all right. And also I will just encourage you guys to, because I cannot obviously do all the variations, right? So try as many variations and stuff you can do. So obviously Brualdi is one book that I have suggested. Okay. But Brualdi maybe gets harder very fast because it's not a book on volume. Like it doesn't have many questions of the same type, right? You can also for practice use some JE book and so on for practice. Okay. And for Olympiad type problems, Brualdi is good. Okay, but yeah, on your own, do as many as you can, as many variations and stuff you can. Okay, that is recommended. Obviously, I'm also trying to do as many as I can. So variations on circular permutations. These are called circular permutations. Okay, these are theoretically also very important questions, but for us right now, they are just important as problems. Okay, basically. So what is the most fundamental question in this area is that you have a circle and you have some chairs, so right now I'll just try to do for general n because you have already seen this last time. Let's say you have chair number 1, chair number 2. Sorry, yes, there is a little bit of dot 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 dot. You have chair number n. Okay, n. So this n is okay. N chairs. N chairs, as you can see, n labeled chairs. So all these labeled, unlabeled obviously matter a lot here. Okay, so one has to parse them very carefully. But I am stating them clearly. So n labeled chairs and n people. Obviously, n people means n different people. Okay, so then the most basic question in this is how many permutations? Yeah, anyone wants to quickly say this? This is just, we know this. N factorial. Yeah, here it will not be n minus 1 factorial. Okay, obviously I don't need to say why, but just saying this just is n factorial because it is n factorial. Okay. This is very simple. Now the the fun comes in when you remove the chairs. So then sorry, remove the label of the chairs. Now they'll just say n chairs. Now when they say n, 1 minute, let's not worry about distance and so on. Just let's say n chairs and equally spaced chairs and so on. N chairs, n people. Now how many permutations? And also let me just say what are the different ways in which n people can seat in these n chairs? Okay, or n numbers can be distributed, blah blah. Okay, so what should be the answer for this case? Obviously we know the answer is n minus 1 factorial. Would anybody care to explain why? And this is a table. This is a table. Okay, now that is important. Anyways, I would want to, yeah. Mhm. This is would you want to repeat what you said again? Because it was not very clear. Just say it again. Yeah, and let's just keep n. Okay, let's just keep 10 men. Let's just keep one kind. Okay, so it's not about, just to make it clear that it's not about different kinds. Okay, just 10 people. Can you just say this again? Just in the language of 10 people without using men or women. And I just want to. Yeah, yeah. but it's not clear what that means. No, the last thing, probably what you're saying is, so I mean, you could say that, yeah, I'm going to fix this person at the top of the table. I'm going to fix one at the top of the table, and then I will arrange the rest in 9 factorial ways. That's the closest I can understand from what you're saying. But it's a bit confusing, right? So maybe you should try to think of it again and write it, okay? Because right now it is not very well organized. Anyways, anyone else wants to say? Again, it doesn't have to be correct, but unless you say, you will not know if it's correct or not. So try explaining it. Because see, you may remember this in various ways, in various incorrect ways, and the answer may still be correct. But once you explain it, it's very important, because then only you can go in the variations. Because if it's not clear, then the variations would. So please try someone, 10 chairs and 10 people. Uh, Now this is a standard formula, we know this, but why is it so? Hmm. Okay, what do you mean by original position? First Saturn. Yeah, so you can understand it's not very precise what you're saying, but yeah, I can understand that you have understood. Yeah, but it's okay. That's okay. So maybe I'll just extrapolate from what you're saying. Is that you take a particular arrangement, because there is no such thing as where they first sat and so on, right? But it kind of makes sense that you will get back the same arrangement. Okay, so I'll say it like this. This is probably again different from what I said last time, but let's do it. I'll just say that take a particular arrangement. Take a particular arrangement. So see, essentially, before I say this, essentially the main reason, if you have to let's say answer this in just one word, you're not able to explain, but you're about to use one word, and that is, if you rotate an arrangement, it doesn't give you new arrangements, right? Rotation. You can rotate an arrangement. Okay, this is keyword. Okay, but the idea is that, look, if you do not rotate the arrangement, so if no rotation is considered, so if you don't consider any rotations, okay, then the answer is 10 factorial. Okay, so what I mean is, if every rotation is different, if rotating an arrangement, if you decide to call that a different arrangement, then there are 10 factorial. You can say this in many other ways, like I'll label the chairs or whatever. That's clear. And now I will say, it is very similar to what has been said already, but still, take a particular arrangement. Okay, by rotating, we can create 10. By rotating, we can create 10 arrangements. Yeah, but all these 10 are same for us. Yeah, so all these 10 different arrangements are actually same for us. We have counted them as different, but they are the same for us, so we must divide. Okay, very simple. Let's say if I just take 5, let's say this, and then this is the thing that you have to learn at this period, class 10, 11, and so on, or earlier, is how do you express, how do you write something which you feel is correct. This is no more a problem after a certain point usually. Okay, but in the beginning stages, this is a problem. So one has to overcome this by trying to write it, say it, and so on. This is the rotation that you do. Again, degrees and all are not important. This, and in this way, you'll get 5 different, 3 more, 5 different. All these 5, we counted them as different, but all these 5 are now considered the same. And so I will divide by 5. Okay, you can just write this. So when you're writing, so maybe prior to doing this kind of maths, we are used to just, the maths paper is more numbers, but that's not how it's supposed to be. So you can write enough words, okay, and people will read it. Obviously school exam will not ask the proof here, but yeah, don't be afraid to write, obviously. Okay, don't hold back on that. Okay, so this is very simple. It's n minus 1 factorial. Any questions? Please clear this, because this is the first step. If you understand this and the variations, even if you read it elsewhere also, you can understand it. But this is very important. Okay. All right. So then let's remove these things. And now there are other ways to say it, these things, but for now this is. So we have n people, n chairs, we have n minus 1 factorial arrangements. Okay. Okay. Now, if I change the object, okay, let's just delete this. If I change the object, necklace. Some of you may have encountered this if you have tried solving more questions in this long time. Necklace. So let's say that you have a circular necklace and you have n, I'll just say distinct beads. If the beads are not distinct, then it becomes a pretty hard question. Okay, but if there is n distinct beads, since we are doing this for the first time, we can just keep it 10 distinct beads. Simple. How many? How many different? No, so that's not the right way. How many different necklaces can be created? That is the question. How many different okay, why 10 factorial? No, but see there, it was n factorial. So it was n factorial not because, so it was 10 factorial or n factorial because the chairs were labeled, and on top of that, the people were also different. So it mattered which person went to which chair. Okay, chairs were like the slots, but okay, but then in the case, when the chairs were unlabeled, then also there were 10 different people, but then it was not 10 factorial. Here it is 10 distinct beads, but the slots, there is no notion of slots, or the slots are not different. Okay, slots are not different. So in fact, this is like chairs are unlabeled because the slots are not different. Slots are not different. Well, there are no slots, but slots are not different. There is no first slot, second slot, and so on. Okay, is that clear to everyone? Okay, that even the chairs were labeled, then it was n factorial because in which chair which person goes. Simple. But here, which slot, which bead, there is no such thing. It is just beads, different beads, but there are no different slots. So obviously we can say bead number 1, bead 2, bead 3, and so on. So yeah, so why is anyone not saying 9 factorial? Is 9 factorial correct? So just like previously it was n minus 1 factorial, here is 9 factorial correct? Sorry. So you can say, yeah, because these 10 distinct beads are like 10 distinct people, and this necklace is like the table. So why is it not 9 factorial, or is it 9 factorial? Okay, so what about others? Okay. Okay, so one way to say it's 9 factorial is if you just use the previous reasoning, right? That let's say that you arrange the beads. Let's take an arrangement. 2, 1, 8. Sorry. 8, 7. So you can, for example, take this particular necklace and you can say, okay, 10 different rotations. 10 different rotations. All right. All these 10 different rotations will obviously give me the same necklace. The necklace does not change, right? If I initially do the 10 factorial, if I initially write 10 factorial where it is static, okay, then I write 10 factorial. Out of those 10 factorial, I am grouping them by 10, right? From here, from this particular arrangement, I can rotate it in 10 different ways. And I'll get 10 different, okay, 10 different rotations, but they are all the same. As necklace, they are the same. But is there any other symmetry? Is there any other symmetry? Is there any other way to move the necklace and keep it on itself again? Is there any other way to look at the necklace? Any other angle from which, any other way in which you can look at the necklace? No. Think there is. You see, it's a necklace, which means that you can look at it. Just think about it, right? You can reflect it. Right? So if this necklace is here, you could be standing here and looking at it, or you could be standing behind and looking at it. And what you would see is two different arrangement of beads, right? It would get anti-clockwise, but they are the same. That's the same necklace. There is, right? To say it in the same way in which I have said so far is that you just take the necklace and rotate it. Oh, sorry, rotate it in 3 dimensions. Is reflected. Okay. You take the necklace and you reflect it. Suppose, so example, one particular, what happened? Yeah. Hurry. Oh, some button got pressed. Yeah. You can reflect it, for example, about like this, right? You can reflect this. You could have not done this to the table, obviously. Yeah. So you can take this, you can reflect it. If you reflect it, what do you get? Let's actually do this one. Is it clear? So this is something new. You see, this is the variations. So one has to understand that, okay, if I'm looking at my object, then how many ways can I move the object around so that the arrangement of beats change, but the object actually does not change. I can actually do that movement to the object. Okay. So they will be considered the same. You would not consider them to be the different necklace, right? After reflecting, you will not keep, if you have a necklace shop, you would not keep those two necklaces separately in your shop. If your necklace does not have a front and back difference, if it's just beads, then it will not have usually. I mean, some other design, I don't know, but just beads doesn't matter. So this B2, what I'm trying to say is the B2 will be fixed, right? But here we will get a B, we'll get B7. Here we will get B1, and this will not be B3, it will become B8. You see, this is the same necklace. You would not keep these two different necklaces in your shop. They are the same. I mean, you would not call them different, right? You won't show the customer these two. They say, what is the same, right? So just think, if you get confused, just think of it like that. But mathematically also, it's there. So mathematically, again, the point is that when you take the static necklace, you put this arrangement, and the question is, how many ways can you move it around and still, keep it on itself, right? The table, you could not have done that, right? You cannot reflect the table, that those two are considered different, unless the table is in space and you're maybe viewing it from below also, and so on, then it's different, and so on, right? So this means, so there are more symmetries. So there were 10 here. How many more then are there? How many different reflections can I create is the question, right? Because each of them would give me the same net. How many different reflections? And you see, these are all different. What the rotation was doing, the reflection is not doing that. Reflection is doing something different. Okay. Five more. Five certainly we can do. We can actually do 10. I can understand why you're saying 5, but it is not 5. Okay? There are actually 10. You have to think. I can understand why you're saying 5, right? You would say 5 because, so actually I made a mistake here. So in the sense that it's misleading, right? So by 5, I understand you mean this one, right? This one, and maybe this one, and what am I doing? There are 10, right? No. Do I have 10? 2, 6, 2, 9. Okay, 2 to 4 to 6 to, yeah, I have 10. So then, sorry, 1 minute, 1, 2, 3, 4. Yeah, so this I will join. And then this I will join, and so on. These are there. These are 5 different, but there are 5 more. There are actually 10 reflections. Find them out. Let's not discuss that now. Find them out. Okay, find out. And then, so this is work to do. Okay, try to show that there are no more. There's no more ways to move the necklace. Obviously, by me, I mean, you can't break the string, and just moving the necklace as a rigid object. Okay, so 10 plus 10, 20, and there are no more. Okay, you have to think. So this time, so those are the things you have to do, okay, to work it out. 10 factorial by 20. Because again, right, we are making groups of 20. 20 objects are getting identified as one. Means these 20 are just the same thing. So, okay. Do the same for, this is the second thing which I want to do. Okay, please do this. Okay, but don't just leave it for this will be 10, so this will be 12. No, do it. So this here the number is 15. Okay, actually work it out, because this is an odd number, so you have to think if it's the same or something changes. Okay, or if you don't want to draw 15, You can draw 15, I guess, but 15 take some 7 something. Yeah, it doesn't matter. Okay, but actually try to figure out how many ways are there to, how many reflections are there. Rotations are obvious. Okay, sorry. So that's an important exercise to do. Please do it. There is more to the structure of these things, but I want to cover the basics for now. And these are what that will also be basic, but I should say core. Okay, so let's not go into the nature of these 20 symmetries and how they interact. Let's just, yeah. So is it clear? Do I need to say anything more? Okay. Okay, is there any questions? Just ask. sorry. So what is next that I want to do? So this was one variation. 1 minute. So we have, yeah, I want to do one more. This is slightly interesting. This is probably my own problem. I'm just saying it will be there somewhere. Nothing unique. We have a rectangle. So now we have a rectangle. We have 1, 2, 3, 4 vertices. So yeah, let's just see that this is a rectangular table and the people are sitting at the 4 endpoints. Okay, how many ways are there to seat? How many ways to seat 4 people? So these are not numbered, chairs are not numbered, okay, but the chairs are only on the vertices. Oh, no, 1 minute. Let me not say this. 1 minute. Yeah, let's just do this first. This is, I think it's good enough for now, and then we'll change. Yeah, what would you do in this case? Okay, it should be why. So like yes, but yeah, but this is a rectangle. So let's just take a situation and see. So if you have, let's say, place the 4 people like this. Okay, you place the 4 people like this. If it was a square, you would have placed the 4 people like this also. It's fine. Here also I place. Now see, now if I take the, use the fact that it's a rectangle, and let's just use our logic, then we can understand very clearly. If I put 4, 1, 2, 3, would you call these two the different arrangements or same arrangements? Are these same or different? They're different. Yeah, so that's why this situation is not the same as if this was a square or a circle, then these two would be considered the same. But because it's a rectangle, you cannot call them, we cannot call them the same. These are different because you could say, in this arrangement, this was sitting together close and this was sitting far. You can say it in many ways, right? It's just different. So they are not the same. So that's why this will slightly different. Let's think how to do this one. For factorial by 2, y2. sorry, 4 and 1 on up. Oh, sorry, yeah, 4 on up and 3 on up. Okay. And where would you place the 1 and the 2? um but how would you go from the first arrangement to the second arrangement? You are right, I think. Yeah, this is certainly correct. I don't know what I'm doing. But no, but there's some, if you just rotate, can you go from here to here by only rotating? No, that's not correct, right? Only rotating you cannot go. There is a twist in this, right? Yeah, that's why I was feeling something is not. You have to reflect, right? You have to do a reflection. Yeah, it's a mirror image. You cannot do it by rotation, certainly. That you can easily see. So if you can get these by mirror images, then are we willing to call these two arrangements the same? Let me also think about this. Should I call these two the same? Hmm. It's a bit of a dilemma. I mean, we should call them the same, as Orgo has said, and because how are you going to distinguish between these two? Because if you look from ah, you are right. I think that's it. I think you're perfectly correct. I missed that. Yes, they are different. So they are different, right? They are not the same. Because yeah, as you said, if you're just on the top of the table, right? Then obviously these two are different, because from one you have to look to the right and get 4, right? And then 4 has to look, and then 1 has to look to its left in this case to see 1. So these two are different arrangements. I would see them as different because there are people involved, right? Yeah, these two are different. Sorry. So there's no division involved in this case. It's just 4 factorial. You cannot do anything. If you do any rotation, then it does not work, and this rotation just changes it. Rotation we just saw does not work, and this is coming from reflection, so also it will not be considered because you cannot reflect the table, simply put, right? And also, as Shana said, that's probably much easier to say, easier way to put it. Yeah, you have to look, but these are obviously different, right? Because one has to look to the right in this case, and one has to look to the left, and so they're different. As necklaces, they are the same. So I mean, in the sense, if it is some sort of a thing where it's a grid and you can look from front or behind, or you can take it in your hand and turn it around, which just means reflection, then it's a different thing. Right. So then it's fine. Now let's actually get to that thing. So is it clear to everyone why in this case we cannot divide? It's just 4 factorial. It's a rich source of problems, and these variations. Okay. Yeah. Any questions? Please make sure it's clear. Okay. So let me just go to that grid case. So now if we just make a problem where I have to grade. But let me not make such questions now. Okay, let's just get to the maths of this. And maths of this is basically find the number of symmetries of a rectangle, right? How many ways are there? Let's just keep this shape, maybe. Let's keep this. The question really is how many ways, how many ways, how many symmetries of this rectangle, okay? But to expand on that, how many ways to move a rectangle in sorry in three-dimensional space. So you're allowed to move it in three-dimensional space. Okay, how many ways? Well, how many ways to move three-dimensional in rectangle in three-dimensional space and place it back on itself? Place it back on itself. Yeah, by potentially permuting the vertices, right? Potentially permuting the vertices. Obviously, not distorting the rectangle itself. Okay, not distorting, not breaking the rectangle and then reassembling and things like that. Respecting its solid shape. Yeah. So like this is one of them, right? So this is one way. One way is to just keep it as it is. This is the most important. Okay, you must also not forget this. And then the other is obviously to do this, is to reflect it about this. And then I'll just say one more, which is probably everybody's seen, is to reflect it about this vertical line. That's another one, right? So if you do that, just draw it in rough here, sketching. You'll get 2, 3. The challenge is are there any more? Yeah. You see, all these movements are solid movements, and you're placing the rectangle back on itself by only potentially permuting the vertices and nothing more. Question is, are there any more? Is there any other complicated motion that we can do which will lead to a different result? Okay, so maybe I should not say how many ways to move, because you can move it in infinitely many ways, but point is how many ways are there to permute the vertices without distorting the shape of the rectangle and only moving it in 3D space. These things are all abstractly studied in what is known as group theory, because we are basically grouping the different configurations of a rectangle, and these are all the same for some purpose. For example, counting problems, okay, depending on the problem. So for example, if this was a table, then you cannot reflect, but if this is a grid where you can look back and front, you can reflect. So depending on the purpose, you can do certain symmetries, and number of symmetries and interaction between the symmetries. All this is studied in group theory abstractly. Well, the real goal of group theory is that, well, this object has these kind of movements. Is there any other object which looks very different, but it has the same kind of movements in some sense? So that is really what they try to do in that group theory. But anyways, are there any other ways? Or no more? If you reflect it diagonally, then certainly it will not sit on itself. So you have to do something more than just diagonally. So let me just do it here. Diagonally, what will you do? Like, so this is diagonal. Now what do you want? If you just reflect, it will not happen, obviously, because 4 will not go to 2. Right. Sorry. But yes, something like that we can do. I mean, we can try to send 4 to 2 and think maybe. Or you can just do it vertex wise also. If you don't want to think about moving the rectangle at once, you can ask yourself, okay, I've sent the one to, like I've sent one to down, one below. I've sent the one here. I've done these two things. Can I send the 1 to 3 where 3 is? Can I send this here? And then what else do I have to do so that everything fits again? So let's answer this question, right? If I send the 1 to 3, then what do I have to do? That's right. Then the 2 has to go to 4. 3's place. That's right. And the 2's place will be 4. Right. Yeah, this looks correct. Right. Can we describe that motion? So if you can take the rectangle, you can or so top, what do you mean by flip it from top to bottom? You mean by this diagonal or something? No. Yeah, I think that's what Pragya also said. Flip it from the top. Yeah, that is perfect. So I was just good job. Sorry. Yes, that is the easiest way to say. Yeah. Otherwise it becomes a little dodgy, right? Is it actually possible to actually do that? Okay. But yeah. So that's very clear that you just basically you compose these two things, right? So you have this, you use this, so you flip it here. So 1 goes to 4 and wait. Yeah. 1 goes to 4, 2 goes to 3. So where is that one? No, yeah, this one. And then in this you apply the reflection. Right. In this you flip about this. Then you would yeah. Right. Yeah. So you get 3, 2, 4, 1. Yes, perfect. That is This is the easiest way. Right. Let me just see if there is some other way to say it. Is it clear to everyone, right? So basically this is just the go-to thing. If you get two different motions, then you try to see what happens if I apply them one by one in different orders or whatever. You may get new motions. You may not get new motions or new symmetries, but you may also, like in this case, we got one. Okay. So yeah, so the one, if I send it this, then basically this one I have to send here, flip, that goes, yeah, it's okay. Okay, so now try to show that there are no more. That there are only these 4. Show that there are no more. This is not difficult, okay, but try. Try to actually write a good reason. Okay, you can do by casework also, but try to write a good reason why there are no more. Okay. See, there are two, but still, who knows? Yeah. See, actually, it's possible that there could be one more. There could have been one more. Right? Like maybe you could say that I will first. So I first reflected by horizontal. So I did horizontal reflection. Then I did vertical reflection. Right, and in this way, I got this one. 1, 2, 3, 4, going to 3, 2, 4, 1. Right, but then like I did these two motions, right, one by one, and we got this. But then you could say, okay, if I first do the vertical and then do the horizontal, there is a chance to get a different motion. You will not get, you will get the same thing. That's okay, but there was a possibility, right? So having two lines of symmetry is not enough. One has to, yeah, having two lines of symmetry means that there would have been one more other than the three that we had. So we had one here, the vertical, and this horizontal, and the one which is just original one, the identity. These three we had. But yeah, having two lines of symmetry means that there should be one more, because if I compose these two, if I do first one, then if I do the horizontal, then the vertical, I should get something new. But then that doesn't mean that there is no more. You could get more complicated ones. So you have to think some other way. Okay. Yeah. So, but the answer in this case is again 4. And the answer is again, you can see a multiplicative number. Okay. You're getting a multiplicative number. Yeah. So you have to see. So these symmetries have an interaction you can already see, right? You're already using the two simple symmetries to discover a more complicated one. Okay. But yeah, they have many interesting things. Yeah, so should we go into more? Let's not go into more variations, but I just want to show the difference between because if you look at a square, okay, and you look at a rectangle, both of them have 4 symmetries. Oh no, sorry, obviously square does not have 4 symmetries. Square will have 8. So how do I think of something that is no, yeah, so let's not say square, or well, I could say this in different ways. So what I'll do is a construction. So what we can do is you can take a square and I'll take a square and I will attach something to it like this. Just a pole. Okay, I'm attaching a pole on one side of the square. Okay, so there are 4 vertices, but then there is also a pole. Okay, why am I attaching the pole? See, attaching that pole, it prevents reflections, right? I could have just said do rotations of the square only, or I could have said it's a table, but just a new kind of construction. Okay, that how you can take an object, just put a geometric obstruction without using words like, make it a table, or putting words like don't do reflections. I can force it in the geometry of the object itself. Okay, so this is just a square with a pole, or with a flag stand something. Now obviously I can only do rotations. Yeah, so this has 4 symmetries, 4 symmetries, 4 motions, and obviously in all of them the 5 is. So here I cannot do reflection, right? If I reflect, then I just goes to a different place. It's no more. Yeah, I can no more place it on itself again. So there are these 4 symmetries. This is the rotations, okay? Only rotations. So what I'll just denote them. I'll use notations for them, okay? So this identity symmetry. This is the do nothing symmetry. So I'm just listing them out, okay? And giving them names. This is 1. And then you have 2. And this is rotate by 90 degrees. Yeah. Rotate by 90 degrees. Let me call this. Now again, just name I'm giving, okay? Let me just call this sigma 90. Rotating by 90 degree. Okay. And then similarly, there is sigma 180, sigma 270. Yeah. What is sigma 360? This is just identity. Okay, so just these notation is just a symbol I'm using for the rotation. I don't want to write the full thing. And so I'm just trying to encode it in few letters so like it's understandable and encoded. Okay. So obviously sigma 360 is identity. Is that clear to everyone? What these notations are? These are just condensed way to write rotate by 90, rotate by 360 and so on. Okay. Right. So these are the 4 symmetries. Now you see what happens. So, okay, let's keep that. The rectangle also has 4 symmetries, right? If you just take a rectangle, we have seen just now. Sorry. By the way, 4 symmetries, the importance of 4 symmetries for us coming from the context is that if it was a necklace, if it was something like grid or something, you can divide by 4 because there are 4 symmetries, the 4 ways to move it, and so 4 different labelings would become the same. So that's why we started this. But now we are trying to just understand that the number 4 is not all that there is. There is more than just the number 4. In the sense that here is a rectangle, and you have 1, 2. Here also we have 4 symmetries, right? Let's just call, so A be the first symmetry. So let A be the symmetry. Let me not use A, let me use V. V is for the vertical symmetry, okay? Which is this. This is just the notation for that, okay? H is the horizontal symmetry. Okay, right? And then obviously there is one which is the identity. And then there is another complicated symmetry, right? What notation should I give for that? Sorry. Yeah. These are symmetries. The question is, how did I get that complicated symmetry? I first use the vertical symmetry. Yeah. Then I use the horizontal symmetry. This is that complicated symmetry. Does everybody agree? So by the complicated symmetry, I mean this one, right? Where this one, where the 1 goes here, 3 comes here, the 4 goes here, and the 2 is here. This one. Yeah, how did I get this? I first had the vertical, then I applied the horizontal, isn't it? That's how I got this complicated symmetry, this one. That takes 1 to 3, 4 to 2, 2 to 4, 3 to 1. You can say it like that. So this complicated symmetry, I will say that first I apply V and then I apply H. This is a composition notation, okay? We will not need this now, so I'm not going into details, okay? This and this. Oh, the point is that these are the 4 symmetries. I can just call this C, complicated symmetry C, okay? So we have these 4 symmetries here and we have 4 symmetries here also, okay? This composition just means V and then applying H. You can just call it C. You don't even have to call it this. Just call it C also. So we have these 4 symmetries. Now, my question is, what happens if you apply V twice? What happens if V is applied or used twice? Anyone? It will return to the same position, right? So V and then V applied twice. It returns to same position, means you get do nothing. So I'm just writing it like this, okay? Right? The fact that if you apply V once and then again, you return back. Similarly, you can check that if you apply H twice, you return back to the same position. And similarly, you can also check that if you apply this complicated symmetry twice, you will return to the same position. Just think, or just do it. Let's not think. Let's just do it, right? Yeah. So again, if you apply this complicated symmetry, what did this do? Just swapped the opposite vertices, right? So again, 1 and 3 will get swapped. That's what it was doing. That is what it was doing, right? So we'll just do that again. And again, 2 and 4 will get swapped. But we come back to the original thing, right? So if you apply the complicated symmetry twice, then also you get back to original. If you apply this twice, you get back to. Now you can write this in words or you can write this in symbols. That is not the point, okay? Point is that these 4 symmetries all have the property that if you apply them 2 times, you get back the original one. That's what they have. But these don't have that property, right? In this, obviously identity has that. I mean, identity is identity. It is just there. It is not moving. Yeah, if you apply the 180-degree twice, you get identity. I guess everybody agrees, right? If you apply 180-degree and again 180-degree rotation, obviously you get identity. But that's it. If you apply the 90-degree twice, you don't get identity. You get 180-degree. So in this way, these 4 things are different, right? These 2 sets of 4 things, they are 4 as numbers, but that is in the richness, in that sense, they are actually different. For counting purpose, the answer will come out to be the same 24 by 4, but the processes that are happening are different. Okay, the nature of the symmetries are different is what I'm trying to say. Okay, that is what I'm trying to say. I will not go more into this about symmetries now because that will take us, but I just wanted to show this, okay, that this is that they have different properties even if they have the same number. Okay, so yeah, right. So that's what I want to do. Yeah. So let's not go into more variations then today. Okay. So let's just stop here today. Okay. I just plan to do 1 hour class today. Okay. Yeah. Obviously Sunday's class will obviously be 90 minutes. Yeah. So yes, please continue solving problems from